Welcome to Sports Sci, where we try to bridge exercise science and sports analytics in R. Today we're going to be building the metabolic power function. This is a function that is supposed to be equivalent to the energy expenditure over time while an individual runs uphill. We see this here. On the left, that is the individual at an angle, where on the left and on the right would be the individual running upright uphill. So we're going to need a little bit of trigonometry, and we'll get into that here. So the torso angle we're going to assume is in line with the athlete's direction of acceleration, and we're going to just use this image on the left where we have a right angle triangle, and we're going to use the tangent and arctangent functions. So we'll be using the mid-sprint package that I've built. You can download it here by copying this or typing this into your console, and let's do that here. I've already downloaded it, so what you would do is you copy and paste it, and then you hit enter. Beyond that, we'll be using just base R. You don't need to install any other packages. So to get started, let's load our packages here. So load packages, there we go. So library mid-sprint, and hit enter. So with the mid-sprint package, we do get some sample data. So we'll look at our sample data, which is our player A. So we hit that and we get something that looks like this. And let's get a better understanding of what's happening here. And we have a speed and a speed column and an acceleration column. How we're going to build this is just step by step to understand how it is. I'm just going to copy and paste the formula here. So there's a few different aspects to this. One is our torso lean that we have to calculate. Two, this is our pardon me there. This is our function here, or formula. So metabolic power formula. So this is it that we're going to be using. There's also another formula that's been updated that does come out to fairly equivalent values here, where we can have that ES is our equivalent slope, which we can get into shortly. So metabolic energy update, let's call that. So we won't be needing this right now. So let's just set that as a comment. So R doesn't run it, right? So if I hit enter, there's nothing that runs here. Whereas if I remove the comment, we'll end up with an error because ES, our equivalent slope, has not yet been found. So let's build the function. Our start. Metabolic power function. As with any function, we start with the name of it. So let's call it metabolic power. We'll save this as an object so we can call it later on. And we have our function, and what we're going to be using is player speed and player acceleration. We open the brackets, and then whatever we write within the brackets is saved within that object, and then we can call metabolic power later on like this, metabolic underscore power, and then you have a player speed, 3 meters per second, their acceleration, 3 meters per second squared, and it'll return the instantaneous metabolic power. So here what we're going to do is calculate the torso angle. So what we're going to do is use the and I'll highlight it here in the on the video. Excuse me. So this is what we're going to be using here. is specifically our tangent. So tan theta equals y over x. This is our y, this is our x. So what we need to do is find that angle. And I'll highlight that, and I'll keep it highlighted here. Let's just close that up a bit. There we go. So we need to find this angle. If we know this angle, we can assume that the hypotenuse, which is this here, and I'll make it a square, that is our equivalent to our athlete's torso angle. So torso would then be our arctan, atan, and we know what our opposite is already, which is our y, which is 9.81. This is going to be in metric, so 9.81 meters per second squared down. And we will know our x value because we're going to assume in our tracking data that it is horizontal acceleration. So we'll have 9.81 divided by player.accel. So that is our athlete's torso angle. I'll just go back here. So this is our this is what we're looking at here, is this right there. But we need the equivalent slope, which is our 90 minus alpha. A lot of times in the literature, you'll see this in degrees. I don't believe it actually works in degrees because I've worked it out in radians, and in R, that's the only way it seems to return the correct values. So our equivalent slope, which we can put down as this, which slope is tan of pi over 2. Pi over 2 is the equivalent to 90 degrees minus our torso angle. Torso, there we go. So let's say the player is accelerating at 2 meters per second. We can copy this. 2 meters per second squared, and we get 1.36. Our equivalent slope would be tan of pi over 2 minus 1 point, we'll round up to 1.37, and we get 0.2. 0.2 would be, if you wanted it in degrees, you multiply it by 180 and divide it by pi, and we see that they're at a torso angle of 11 degrees, which intuitively makes sense. Usain Bolt at max acceleration is about 45 degrees. So from there, we want our metabolic energy function. So metabolic energy is just the total amount of energy expended. And then what we're going to do is, so that those will be in joules, and then to convert it to power, we're going to put it over seconds. So joules over seconds is equivalent to watts, which is the which is what power is calculated in. So metabolic energy. So I will copy and paste this here. So this is the first part of the formula. Is, let's remove that comment. This is the formula within our equivalent slope, where we see that if the athlete is not accelerating and is completely upright, moving at a constant speed, they are expending 3.6, I believe it's joules per meter per kilogram. I might be wrong about that, probably am. And then what we do is we multiply by 1.29, and that is to make up for the fact that grass is not a frictionless surface, so it does increase our energy expenditure slightly. To then go from metabolic energy to metabolic power, what we're going to do is multiply metabolic energy times the player speed. Let's make that a little cleaner there and toss that on another line. And then what we want is to return our metabolic power. So it's very simple. You hit enter, and now you have our metabolic power function, what we can do then is copy this and input that other formula here. And this is just an updated formula that's been used with soccer players. So we can just replace all of this with that value, metabolic power update, and we can hit that. So let's assume that, so we'll hit example. So speed is going to be 2 meters per second. Excel is going to be, let's do it where they're near max speed. So max speed would be 8, acceleration would be about 0.2, for example, and we get metabolic power here. You can just hit enter. Player speed is 8, 0.2, and we see that it returns 41 watts, which within the literature makes a lot of sense. We could also hit metabolic power update, so 8, 0.2, and let's replace ES with equivalent slope. So ES. All right, we'll just have to hit enter again. And so 40.3 and 41. So we see that they're fairly similar. This is up to you what you want to use and apply. So let's add this to our data table, or data frame. So update data frame. So we know that, again, player underscore A we have. So let's add metabolic power, met power, and we're going to use metabolic power. We won't use the updated function. It'll be somewhat redundant, but it doesn't really matter in the end. So metabolic power, we have player underscore A for player speed. There we go, and we can hit speed, and then player underscore A Excel, and then that will return an updated data frame, so we can look at that. Head player underscore A, and there we have it. We have metabolic power. So this is going to be instantaneous power. So what we will want is our cumulative power. So player underscore A cumulative metabolic power, and then we're going to use the cumulative summation function. So sum, and then player underscore A metabolic power. And then what we have here is, we'll check that out again, player underscore A, and we see that this is now adding up all these individual values in metabolic power. So let's visualize this. Viz. So let's just do plot, and then we have, actually, let's do this. We'll add some a time variable as well. So player underscore A, let's go duration, and then we'll just go 1 to n number of rows of player underscore A divided by 10. So let's assume it's at 10 hertz. So now again, there we go. We have a duration. So plot, we'll have on the x-axis duration. On the y-axis, we will have metabolic power. Our data is player underscore A, and that should object dir is not found. Okay, so let's do it the other way around. Met underscore power onto duration. And here we see that the player didn't really do all that much until the 140 hertz mark, or 14 seconds in, where they have this huge explosion. This is not uncommon. What we can, sorry about that. What we can see is metabolic power. Metabolic power. If somebody is moving at near max acceleration, so we'll have 15 as our acceleration, but we will have 0.3 meters per second, we end up with these massive values, which makes sense. They're instantaneous for 0.1 seconds. So let's then plot our cumulative metabolic power output. So metabolic power cumulative onto duration. Our data is player underscore A. I used the wrong variable name rather, met underscore power. And there we go. So we see that, this player is moving fairly regularly at a constant speed. Then we have this big jump and moving up again. So that's all there is to it. This is the metabolic power function. Very simple. And you can add it into any of your existing data frames where you have the player speed and acceleration. And as long as you're okay assuming that their torso angle is equivalent to their rate of forward or horizontal acceleration. And as a little plus, we can also see that metabolic power, if they're moving at 2 meters per second, yet they're decelerating at -2, we still get this output that isn't the same, right? So 2 meters per second accelerating at 2 meters per second squared, we have a lot larger output than if you're decelerating. If you have any questions, feel free to reach out to me on Twitter at Aaron Z. Pearson. You can also reach out to me directly over email, aaron@midsprint.io. You can check me out at my blog at midsprint.io. And I hope you enjoyed it. Thanks.